Okay, so the stuff that I had you read over is this concept of design rule checking and how you actually, we've kind of alluded to it with Lambda design rules. So how do you actually use these tools to actually do this for you? So the first one was static and dynamic analysis, where static analysis is you just pick test the circuit, and then dynamic analysis, you actually are putting in inputs to it. And then the design rule checks, you're actually doing this physical placement of the layouts, whereas ERC, which is your electrical rule checking, is checking the properties of the circuit, and we're going to be going a lot more into that in the section 8 as well, especially when we get into tape out, where you're actually making sure that your wires and everything are properly spaced and that you're properly you're properly distributing the CMOS throughout the chips. That way you're not consuming too much power in one area and potentially degrading it over time. So then you got functional and timing verification. So node extraction, which you kind of learned a little bit about, being able to take a circuit and you generate a SPICE file, right? So that's your actual nodes. And for those of you who went in, did some stuff, deleted some nodes out and put it back in to try to get it working properly, you probably noticed that the nodes weren't properly connected, so you actually had to go into the SPICE file and actually fix those up. Polygon-based node extraction is based on the sizing, and raster-based node extraction, you kind of want to take, when you had all those plot points and those dots on the graph, and you're doing your NAND gate and you're laying it out, and you want it to be a specific size, you're doing raster-based node extraction. And so this is kind of an example of node-based, and you're actually kind of going through here, and you are doing a design rule check. It's going to move along, and then you make sure that along each little area, you're kind of making that it meets a set of rules. So it's going to eventually go over the entire design, going to move through that way, kind of in this manner that it's talking about here. So polygon node extraction, as we kind of alluded to, transforms polygons for analysis. So you want to convert them. In this case, it's along horizontal lines. So if you have your polys and your vias connecting your NMOS and PMOS, right? And so you have some input, and then you have the flow to the output. These polygons are then converted in that manner. So the whole goal of these polygon and raster-based extractions is try to reduce the time it takes to actually convert your circuit to test it. So there's design automation of rule checking. You want it done as rapidly as possible, especially when you get millions and millions of transistors. These kind of challenges become important. So we had this network consistency checking, where basically you're comparing the two networks of associated individual components. And we gave an example of where NCC comes into play. These are, you have a NAND gate, an inverter, and feedback, right? And so this is how it's conventionally laid out. And so you have your output. But also you might be able to lay it out like this. Like these are logically equivalent circuits. However, in the concept of physical layout, they're different. You have some wire overlapping here, you got some feedback, you got all kinds of issues. So we briefly talked about graph isomorphism. It's basically taking your polygons and relating it to graphs. We'll discuss this in a lot more detail in section 8. We'll talk about hashing functions and how to do all that. Basically, the whole idea is being able to take the connectivity of inputs of specific cells and being able to lay them out properly in the circuit. We then touched on merge. So I think I have a chart here, right? So you had merge, which is combining overlapping polygons on the same layer. You have a union. Once you've actually checked that, then you move it up to the next level. Bloat expands all polygons in a layer by a specific distance from their center. And it specifically accounts for AND OR gates and XOR gates. Ultimately, you want to use these polygon-based DRCs to be able to determine error and how much space you need. So, for example, we had this equation here where you have your poly 1 and the minimum space that you need to have divided by 2, and then the second polygon with the minimum space divided by 2, and you AND it, and that's how you account for your bloat. So here you have these two polygons, so poly 1 and poly 2. And so your original polygons are such. Now your bloat, so the original polygons were inside here, right? And so that's where this bloat comes into play. What we've done here, I'm sorry, bloat's this. So then we account for the bloated polygons, and then we find the intersection of the bloat there. So you merge those two areas, and that's your error right here. And so that's what that's how you work on it. So basically, and remember we have the lambda-based design rules. You're supposed to have a specific distance, so 2 lambda, let's say. What that ends up meaning, the reason why they do that is so that way you can avoid this. So if they had the 2 lambda and it been over another lambda, then what would have happened is they would have had bloat, and the merging of the 2 bloat areas would have not existed, and therefore you wouldn't have had an error. And so a lot of this, as you've been running this, you probably noticed that sometimes it can take a little while. So the reason why we tried doing these raster-based checking and these different ways of kind of scanning across is because doing it, if you're trying to do like P threads and trying to do it in parallel, trying to get certain areas, it can be very memory intensive. So there's trade-offs between what kind of system do you have versus how fast do you want it done. And so again, working set polygons, kind of taking this raster-based approach and then comparing neighboring polygons, sorting edges along one axis, whether it's the x-axis or the y-axis. And so what's happening here is that it's moving across this specific design, and as chosen the y-axis. So as it moves along, you see how here it's hit all of these different polygons. So it's going to do DRC checks on those. And as it moves along, now it's hitting all of these, and then it moves on a little further, and it's only doing those, right? So the whole goal is we want to minimize the memory overhead that we're doing by trying to, eventually when we get over here, it's only this last one, it's going to have this one and this one. So the whole goal would start over here and do this one, this one, and this one. And the objective should be, especially if it's already solved the problem, it can then cut this out. You know what I'm saying? So the goal is to try to make it less memory intensive. So hierarchical DRC. So basically now you want to try to create a full adder, and you're trying to build smaller cells into larger cells. So here we've designed AND gates, we've designed an OR gate, we've designed XOR gates. So now we're putting those cells into a bigger cell for a full adder. And so if we create the 2 cells and they're the same, right? So we call a second instance of a cell. We have the same. We have the same tech file. It's running the same temperature. You know, we have the same. You have the same .include file, so it's the same technology size, and you create these similar. So basically, if you've checked this one successfully, then the rest of the cells you just kind of focus on the higher level, because there's no need to check the same cell over and over again. Obviously, how the wires connect between them, you need to check that, but that's on that next level of the hierarchy. So we had talked about these electrical rule checkers, and that's kind of where we're going to talk into clocking considerations. So remember we talked a lot about in order to reduce power, we have the manipulation of these pull down networks, and we had a lot of where the VDD is actually connected to a clock. And so what's actually going on here is we have, in order to estimate power consumption, we have two inverters, right? And these two inverters, in this case, you'll recall, we're actually trying to reduce power consumption because we tie the gate, the drain of the VDD to the gate, right? So what ends up happening is that we can use this inverter by using this phi value. You recall this allowed us to have a smaller size. So but here's the issue: is now you have two different timing signals, and so one of the two they won't be active at the same time. It can be estimated to using the power of only one pull-up, right? So if we have phi1 consumed power here, so it's consuming power here, then phi2 is offset, right? So then power estimation is based on the specific timing. So here, now we've actually put them together. So they are guaranteed to never be active at the same time, because what's going to happen is you need to put a 1 here, right? You put a 1 here, it's going to give you a 0 on the output. Put a 0 on the output, that means the NMOS is not active. So here, what it means is when all the heuristics are exhausted, it must be assumed that the remaining pull-ups are active, since their state is data dependent. So basically what's going on here is then now you're using the tool to try to figure out how much power is being consumed in certain parts of the circuit. And when you get into these concepts of PVT corners, you really have to worry about whether or not your circuit is consuming too much power in specific areas, because what ends up happening is that if you're constantly using one part of your device but you're never using the other part of the device, then you can't. And over time, you have your laptop, you have to make sure that your energy use is distributed properly. Otherwise, you're going to get burnout, but you have all the rest of the CMOS that's hardly been used. So that becomes a challenge. And then last, certainly not least, you got this transistor ratio checker. Seems pretty intuitive. The whole idea is you actually just make sure that remember all these calculations you did in previous sections, and then for exam 1, you had to worry about making sure that you could meet, you had to get to your noise margins, and you had to make sure that you had to worry about path effort and logical effort, and when you put these devices together, how do they actually work? So you have these transistor ratio checkers to make sure that your inverters or your buffers that you're using to restore the signal on these outputs, like we calculated. Remember that one problem where we had either one inverter, or we had 3 inverters or 4 inverters, and you had figured out which one you should actually use based on a combination of sizes and being able to meet certain design constraints. So these transistor ratio checkers do that for you. They make sure that you're actually meeting these requirements. So that's why I say whether appropriate relative scales or ratios of the driving components are met in order to achieve proper logic transition. So you now know how that's actually being done underlying with the math. Recall from section 7, that is section 6. I should add into that. But basically the whole idea is that you have this rising and falling times, and you wanted your rise and fall times to be similar, or as close as possible. So you have our propagation delay falling here is 3.1 picoseconds. The propagation delay rising is 3.6 picoseconds. So time falling is 2.5 and time rising is 3.5. So we have a little bit of some issues here, right? With the imbalance between rising and falling times, to ensure a circuit will operate correctly, analysis of the relative transistor must be done. So here we had, this is a layout of a classic inverter, right? So in this case, we'd worry about with the diffusion size. It's 8 to 4. And here we're actually trying to make sure that we have some sort of constraint where we actually, it's not just the normal 2 to 1, right? It's driving some other circuit. So here we have our input, and then we have our our output is driving something else. So as a result, we have to make it 4 to 1. And so there's actual command in SPICE that you can actually use to do this, .opt range, to determine the appropriate ratio to optimize the rise and fall times. So basically you do why can't I remember the words? Basically you do the analysis, a Monte Carlo analysis, and you can use opt range, and the goal is, okay, well, I need to make the transistor this size. It's going to go over, it's going to take the NMOS sizes and grow it from certain range to certain range. So you have to make in your SPICE file, you make the width a variable, and then you do the Monte Carlo analysis with opt range, and you hit a specific, and what's going to do is compare your rise and fall times of your device, and it's going to say, you need to make your NMOS this size in order to make your rise and fall times, your propagation delays, optimal. And so I included these Lambda design rules that we used throughout the most of the course. And so the reason why I did this is, remember when I presented these, I said, well, these are the fundamental ones, but when you get to your specific design rule checker, they're going to be different. So this is how they're actually different. So MOSIS uses this scalable CMOS rules, and these are the ones that you've been using so far in electric VLSI. A set of logical layers together with their design rules, which provide a near process and metric independent interface to many CBROS propagation rules. So if you recall, we had this Intel 90 nanometer and 45 nanometer. The Lambda design rules don't really account for this very much because they focus more on, they were developed when you had 0.3 micron, 0.18 micron, but now we're getting lower into like the 90 nanometer, 45 nanometer, where we have to worry a lot about more than metal 1 or metal 2. Here they have 90 nanometers up to metal 6, and you have metal 8 and 45 nanometer. We have to worry about that more and more. The Lambda design rules become more important. So this scalable CMOS rules. I included a link, which if you for whatever reason you really wanted to dig deep into that. So you can go into, this is all of the rules that they're using to determine whether or not, all these different designs based on what you're reading in. I've included the specific ones that I feel like are going to be useful for you as you're moving on, like the minimum width and the minimum spacing between wells at different potentials. So this is kind of a diagram that lays it out. When you look at it, 1.2, that refers to rule 1.2. So standard, so scalable CMOS is going to be 9 lambda here between two different N wells. So for some reason you have to split up the N wells. You have to separate them by 9 lambda and so forth. So you see 1.3, minimum spacing between wells at the same potential. So what this means is, for some reason, does anybody remember the concept we talked about where we had 2 different VDDs? We had a converter, so we had VDD 1 driving an inverter, and then we had a second one here, and it's actually driven by a second supply voltage. It's starting to look familiar. Do you recall which one had to be bigger in terms of VDD? Want to be DD2? Why? I'll give you a hint, noise margins. So what's going to happen is you have some sort of noise margin here, and you have another noise margin. Let's say this one's smaller. So if you hit 85% of your noise margin here, right? And then you have this one, and then you are somehow magically in here, and then you can go back down. So you were correct, it was 1, but that's why. So now this is where it's in practice. So your active regions, you have your distance between, here this is rule 2.3, source drain, active to well region, right? So source drain, and you have a second source drain, so now it's like an inverter, right? So now you're keeping your P and N regions separated. You have your pull up and pull down networks. And so rule 2.4 here is substrate well contact active well to edge, right? So we have some sort of output here. And so here they made it 5 lambda, here they made it 3 lambda. And then 2.5 is the minimum spacing between non-abutting active of different implants. So basically what's going on here is that you have some sort of different dopant, right? So for some reason they have flipped this. They see they have the N well, and then for sizing, what they've done, you see how they've actually flipped the PMOS and the NMOS here in some sort of different sizing based on different active size here. And so as a result, you need this distance here of 2.5. to make it work between the active ranges. Does that make sense? Yeah, the reason this is done, everything we've done up to this point has been the pull up and pull down networks have been, their geometry has been the same, but sometimes you may have something like this where, this is not a great drawing of it, but for in order to get the geometry to work and be able to optimize power consumption, you actually can flip it around, and as a result, you need a specific space between them. And then these are your poly rules, so these are just like how do you get the signal through an active region, right? So here, it's pretty similar to scalable CMOS. It's pretty similar to everything. Remember our lambda, we had 2 lambda. The only thing is minimum active extension of poly. So let's look at 3.4 real quick. The 3 lambdas, you need the minimum extension of lambda over poly. It needs to be 3 lambda here. You remember in the CMOS transistor in the inverter, we had a poly, right? And we had to have an active region go over it. That's what that is. Okay, so I'm going to kind of skim through this. A lot of this is already on Blackboard, but I want to make sure that if you give me the opportunity to have any questions, I'm going to go over full adders and I'm going to go over the basics of the MIPS data path. For those of you who had me for 385, it'll sound very redundant. For those of you who didn't, basically the reason why I'm including it is because when you do your Lab 2 and Lab 3, you'll be doing a lot of Verilog, and you'll be expected, we're going to be doing something a little different. We did single cycle and pipelining. Basically, we took a single cycle and then we split it up into stages. What we're going to be doing is one that's different. It's called multi-cycle, where the whole idea for single cycle, you'd have your 5 stages and it completes it in this time. And then pipelining, you have your 5 stages, but you're able to do things in different times, right? So we learned a lot about how there's a tremendous amount of overhead. So there's a compromise called multi-cycle, where you actually, if I only need 3 stages, I only do 3 of them. If I have load word, I need 4. So it'll cut down, it'll be less than single cycle, but it requires a little bit more overhead. So, branch equivalent order requires 3, store word requires all 5, and so on. So we're going to be doing that, and you're only going to be, most of the Verilog has been provided for you. What you need to go through is you're going to be adding an add-I instruction. So you add immediate. So the addition, you take 2 outputs. Well, I mean, okay, we'll go over that in a bit, but it's not as that's not going to be super terribly intensive. So 1 adder circuit, it's important. 1-bit full adder, include the to actually draw the circuit out and the equation. So you've got 2 XOR gates because the sum is A XOR B XOR C in, and then C out is AB XOR C and AB. So you got the AB here, and they go there. So that ties into that. So here I've included a small full adder Verilog code. So you've got our full adder module. So we have our inputs and outputs. And we had to create our wires, sum and carry, right? And so a simple version, in 385, I made the constraint that you had to do gates, right? Because I was really emphasizing scalability. In this course, I'm not going to have that constraint here. So you can do the sign where you have sum is A XOR B XOR C, and then you can do this as well. And then what the design is going to do, with the design rule, the design automation tool, is actually it's going to make your full adder and CMOS come down here, right? So if you were doing, this is kind of a dual A and A naught, C and C naught coming in, and then you have your sum and then your carry out, right? And then what's actually going to happen is it's going to take your design rules. It's going to take all these, how do you actually size these transistors, everything we've learned up to this point in this course, and it'll synthesize it down to this. So you have these poly. The poly, we've learned a poly so far. Everything we've designed is going this way. In this case, the poly is running horizontally, A, B, and C in, and then you have your sum output. Yeah, so you have your carry out here. So you got these pins that are, okay, so you have VDD at one level, you have another level of metal, you have poly, and then you have all these different interconnects. But the goal is you should be able to activate, if you hit A and C, right? So A XOR B XOR C becomes, you should be getting a 1 on the output. So you're actually getting your output connecting here to the sum. So you see how everything's connecting to sum here, and yeah. And then you got your carry out, which is being affected over here. Does that make sense? And so in 385, I kind of went over this concept of a ripple carry adder, where you have at this point you all know this, where the carry out goes in the carry in the next one. So part of the hierarchical design is that once you've checked one of these cells, instead of using this raster-based design and having to check another cell and having to check another cell and having to check another cell, if you're reusing the cell over and over again and you know it works, then there's no reason to actually check it again. So instead, what you're doing is you're just checking the wiring, and that you're actually meeting the power constraints, and you're actually meeting all of the you're reading all of your regions, your noise margins. So that's where this hierarchical design and that Gasky-Kahn chart that I always present at the beginning of my classes. The reason why that's understanding that is so important is because now you're significantly cutting down on your design time. So then I also talked about this ripple carry adder. So you can actually design a cell of a 16-bit ripple carry adder, right? And then you used you've got a 32 to 16-bit multiplexer where you use the last carry out as the select line on a MUX. requires more area, but it's faster. So again, where these design rule checks are, you checked a cell, then you check the 16-bit cell within that to make sure that it actually works. And then as you're going through this level of the hierarchy, you're just checking the multiplexer in these wires to make sure everything works. So all this is meant to cut down and reduce the time that's necessary to synthesize. And so comparison to ripple carry, carry select, and carry look ahead. Does everybody here not know what big O notation is? Okay, so ripple carry just basically means that you requires n computations. If you have 32 inputs, it requires 32 computations, and it requires 32 full adders. Carry select is a square root of n because you go back up here, you're actually doing the calculations together, so you're reducing it, right? And then you use this one last output. So instead of having to do these next 16 calculations and wait on it, you're just cutting in half. And it has a slightly larger space complexity because you have to make another 16 bits. That's 3 halves. So for those of you taking algorithms, you know that just brings it back down to big O of n because any constant ultimately is the same. So carry look ahead has the best execution, so it only takes log n of time. So if you have 32, it's going to be just log 2 of 32 is going to be 5, but it has expensive space complexity. So in 385, I kind of just said, yeah, that's a thing, and we won't really go into that much detail about it. In this course, however, we will. So this is where I want to get into more detail. So how do we actually obtain that log time, and how does that actually tie into CMOS, and why is this important? So what's going to happen is if you have 32 bits, you're going to have all these propagate and generate cells within these full adders. And so what happens is the full adder is dependent upon the carry signal. So what's going to happen is based on the inputs that's actually getting, it's actually going to predict the carry signal by it doesn't even require the rest of them. And the way it does that is it's going to generate a signal and then it's going to propagate it. And then the third part is kill, where if it decides it needs to be, if it predicts a 1 but then realizes it should be a 0. So the generate carry out is 1 independent of the carry in. So that's generate is A and B. Propagate, C out is going to just be equal to C. That makes sense. You're just propagating the signal. So then here they have A XOR B. So they're going to have a G, P, and K in this. So you have A and B, you got A XOR B, and then kill is not A and not B. So the logic you're going to get in, you need to be basically 0 regardless of what the carry input's going to be, and it's using that to propagate. So if A and B, if kill is 1, that means we have an instance where A is 0 and B is 0. Because regardless of what's going to happen, you get a carry in, you're not going to get a carry out. Does that make sense? So it's basically what it's doing is it's taking the logic from an adder and figuring out what do we explicitly know. If we know that we have a 1 and a 1 on A and B, well, you're either going to get a carry in and you're going to have a carry out, or if you don't get a carry in, you're still going to get a carry out, right? It just, see, if you're adding 1 and 1, 0, 1 and 0, 1, you're going to get 1, 0, so you got your carry. Or you're adding 1, 1, and 1, right? Either way, you're getting a carry bit. So we can determine that. But if you have 1 or 0 and 1, then it ultimately depends on the previous carry. So that's where that comes into play. And so this was used to develop something called a Kogi stone adder. So when you do your lab, you're going to see that my history is going to be on this guy named Peter Kogi. Peter Kogi he's a professor currently at the University of Notre Dame. If you go into honors, he's with IBM Federal Decisions, and so being appointed an IEEE fellow is a big deal. Basically, he is also the guy who he basically invented pipelining. And I had the opportunity to meet him a couple of years ago, and he actually had the first pipeline chip just on his desk. And my advisor admired the heck out of him, so I got a picture with him and sent it. And my Ron goes like, "Oh, Peter Kogi, wow, very impressive." So basically, this guy not only did he do everything with pipelining, he also managed to figure out the theoretically fastest adder you can do. And so he generated this idea of propagate, generate, and kill, and then this Kogi stone adder. Here we go. As a parallel prefix form where we're taking these generate and propagate signals, right, and using them to predict based on logarithms to be able to figure out what the carry signal should be. So that way, instead of having to wait until this is done, instead of relying on all 32, it may only rely on 5 if it's a 32-bit error. So here you see 0 is going to 1 and then 3, right? And a lot of these, they just affect the next one. So what ends up happening is you stretch this out to a 32-bit carry bit adder. It's only going to be 1, 2, 3, 4, and 5. So that's where you're actually able to predict the carry bit in the log of base 5. But as you can probably see, this adds a lot of space complexity because these propagate and generate bits, they add up over time. So if you're trying to go through this in CMOS and you're trying to do raster checking, well, it'd certainly benefit you to have already checked all of these cells. Otherwise, you'd be going through here, checking this cell, checking this propagate and generate cell, determining all of this, right? So that should significantly reduce your time. And so these become the logic that's generated as a result, right? So what ends up happening is you are able to reduce the logic from your carry to be able to figure out what the minimum should be, and as a result, that's how you're able to generate the propagate and propagate and generate signals. So the other challenge is, well, let's say I want it fast, but I still need this design constraint. So we're going to talk about this concept of sparsity, and sparsity becomes useful in CMOS as well. So sparsity is, okay, well, I can cut out certain ones of these. It will reduce the speed up that I get because I'm ultimately dependent upon more calculations before. However, it reduces the area and still speeds it up. So it's a trade-off between this space improvement in runtime and space complexity. So understand these two concepts of radix of the adder refers to how many results of the previous level of computation are used to generate the next one. So in a fully designed Kogi stone adder, it's 5. It also ultimately would be 5 because remember it's based on the logarithm, right? So here, this is 16, right? So here, I'm sorry, let me scroll back up here. So what's going to happen is you're dependent upon 1, 2, right? So here is 1, 2, 3. See how these kind of flow? And then if you have this full thing here, you got 1, 2, 3, and 4. And so that's the longest path. So that's the one that you're most dependent upon. So if you're actually able to cut this out, you're actually able to do all of the adding with a sparsity of 4 instead of the full 16. So you're actually able to significantly reduce the area. You just lose a lot of the speed up, but you don't lose all of it. Does that make sense? And from a CMOS side, well, that goes good because instead of having it this big, we're now cutting it down to probably about that size. So less area, runs faster, reduced power consumption compared to the full Kogi stone adder. But then again, if you're getting down to your normal full adder, it's probably about that size, but it runs a lot slower. So this is where good design requires good compromise comes into play. So this is obviously a lot easier to check and a lot less resources intensive, but it may not meet the speed requirements that your customer wants. This will do it. It requires a little more area, costs a little more, but it's a good compromise. But if the only thing they want is fast and they don't care how much it costs, they don't care how big it is, then you have your optimal speed. Okay, so the other thing I want to kind of go over real quick is who's bugging me? Oh. Friend asking me a political question. I don't care. Go away. I just want to do science. Donald Trump can claim things don't work. Doesn't matter. The world will say it does. Okay, so I want to kind of also quickly go over how SRAM cells work. So basically, in MIPS, we talked about how these registers will dual read, single write SRAM cells. And so this 7.21 is a 6T, which means 6 transistor cell. So we have 2 inverters here, and then they are both controlled by 2 NMOS gates. So what's going to happen here is you got a word line, right? And so we know that NMOS transistors are activated when we have a 1 on the input. So when word goes high, both of these are activated. And so bit and bit bar are opposite. So going back all the way to section 1, what is NMOS a good conductor of? Yeah, NMOS transistors. So we think, okay, so that's where we put the value on the gate. What is it a good conductor of? Zeros. Why? Because of,
well, the one pushing down.
Yeah, there we go. That's right. One's pushing down, so you're able to create a conduction channel of zeros. So what's going to happen is, if you have a 0 here and a 1 here, right? So let's say we can actually now go through the circuit and figure this out. So now this is going to be, they won't flow through here. So what's going to happen is you have a 0 coming in here. You put a 0 here. So now it's going to go to the input of this inverter. It's going to activate this PMOS. That's going to turn up. It's going to put a 1, and you have you have created your channel, your inversion region in PMOS. So you have a 1. So it's going to put that here. This one puts those here. So now it's going to activate this NMOS transistor and allow the 0 to continue. So it's going to strengthen this 0 here, and it's going to keep looping. So that is how we use sequential logic to maintain memory. So every time it goes through, it eventually reaches equilibrium, but that allows it to have a strengthened memory cell. Same thing, we do word line at 1, and then we put this one at 1, and this one at 0. What's going to happen is go through the inversion region. We have our MOS here, so it's going to go through here. We have our goes here. We put 0 there. We activate this PMOS. That creates this inversion region, goes through this cell, the one there, which activates this NMOS, puts a 0 through here, creates a conduction region, and we have our 0 again. And then again, we go through our loops. So that's how we actually use those to do memory. So we actually are able to, by flipping between bit and bit bar, we're actually able to generate either a 1 or a 0 on the memory. So if we want to think about if we want to change it, then that's how we actually get our bit and bit bar flipped. So what's going to happen is it continues to hold the value. So we put word line at 0. Well, then both of these are off, and then it's just going to be based on this output and this output flipping back and forth. So if you remember, for those of you who took 385 with me, the register write signal is going to be tied to word line. And then bit and bit bar are going to be the actual input signal that we want. So that comes from the 32-bit value that's coming from the ALU or the data memory, right? And so this pretty much describes everything I just told you here. Oh, well, this is an SRAM read, so you want to be able to take on the word line. You can't have it flip, so what ends up happening is it kind of comes up, it doesn't avoid the noise margin, it comes back. So being able to, this is what's physically happening when we actually read the SRAM cell. And so SRAM write, this is what I just physically described. This is what ends up happening. You got the word line changes, and then eventually when it happens, a bar comes down and an A will respond and come up based on, and there's a little bit of delay. They don't happen at the same time because we actually have to worry about, right, well, so you have the one put at a one inverter has to affect the output of the other inverter, right? So that's why they don't happen simultaneously. And this is just a little thing I've included. CMOS level, the way it's designed, 26 lambda by 45 lambda. And there are people who they have dedicated their entire careers to figuring out how to reduce the sizes of SRAM cells. And so I wanted to, I think the next thing should be the SRAM stick diagram, right? So the one in the middle is for SRAM. On the right is 4 SRAM cells utilizing layout overlap. So remember we talked about this layout overlap concept about, I said you can actually flip these. Let me see if I can get it to zoom out. There we go. So we had, this is the actual layout, and this was the design stick diagram. So you can actually see the inverters here and how they're, and we actually have an NMOS transistor there on each side to play with everything. So what's going to happen is this is the way it's actually going to look when you do it in electric VLSI. And so then this layout optimization, see how we actually have the pull up and pull down networks. You see how they're actually flipped. So this way is that if you compare these two cells, like the pull up network is here and the pull up network is here. And I described that. So if you actually had them, you couldn't do this the other way, and you'd have to make it longer, which would increase your wires and increase your timing delays. So by flipping it that way, you're actually able to reduce the, I mean, it's the same amount of area. However, you're actually by reducing the wire length, you're ultimately reducing your power consumption and your interference. That's just why I said they're utilizing layout overlap. And so dual read single write is what happens when you have 2 word lines. So this would come from, we have the values from 2 registers. So the way it'll work, and we'll talk about MIPS in a second here, but you had your 5-bit input and it converted to as a 5 to 32 decoder, and you had one line here, and you had a second one. And so this is 5 and this is 32, and each of these went to one row of SRAM cells. So what's going to happen is this is going to be your word line that goes to that one, and this one comes out here and goes to this one. So if you had a case where you had some sort of instruction where B equals A plus A, right? I need to get that value twice. And so it's going to access it both times and being able to read it both times. So that's how dual read, single write actually works. And so going over MIPS MultiCycle implementation, I kind of I did allude to this earlier in the lecture. So for those of you familiar, MIPS single cycle is a 5-stage as instruction fetch, instruction decode, execution, memory, and write back. So the whole idea is you want to be able to get an instruction, get some values from registers, process them in the arithmetic logic unit, and either put it in the data memory or you want to write it back to the local register copies, which are the cache and are faster. By splitting it into parts, we can have faster clock rates. And so when I say different instructions take a different number of clock cycles, I'll show you this finite state machine that's used as the controller. In single cycle data path, I showed you there was these 6 AND gates that are used with different negations on the input to be able to determine the correct control signals. In multi-cycle, your trade-off is you're going to have a much larger controller. Functional units are more than one. So remember in MIPS single cycle, we had this concept of control hazards. And the way we did it is we separated data memory and instruction memory. In multi-cycle data path, they are together. And we're going to be using them multiple times in the same instruction. Now, we'll show you how to do that. And so as a result, we only have one ALU and only one memory. And then we specifically have 5 registers added on top of what's normal. So we have this instruction register and this memory data register. So the memory that we have, we split it into instruction memory and data memory. So if we have an instruction, we want to call an instruction, we store it, the output there, and then we use a control signal to determine whether it's an instruction or it's a store word or load word instruction. And then we use a control signal. And on the outputs at different stages, we just have inputs for A, B, and ALU out. And so for review, for those of you who, I know this is going to sound really redundant for those of you who have 385, for those of you who haven't, there are 3 types of instructions in MIPS. Register, immediate, and jump instructions. The way it works is a register takes 2 register values, performs some sort of operation on them, and stores the result back in the register. So RS and RT are the 2 result registers that you're going to do something to, and the 5 bits, there's 32 bits in MIPS, so it represents a 32 bit value. You grab this register, you grab that register, perform some sort of operation, which is this opcode here, and then you store it in this data. This value is a shift amount, meaning that if you need to do shift left or shift right logical, it can tell you up to 32 bits what to do. And then this function here is used to differentiate between different types of R-types instructions. So I mean that you'll see this in this table here. Immediate values use one register, either have some sort of data transfer function. So either if you're doing an add immediate, so if B is equal to A plus 1, what's going to happen here is this will be A, and this will be a binary value of 1. You perform the addition, and you'll store B, which will be in this register here. And then jump, basically, if you're doing some sort of, or you can actually do branching. So if you have an if statement, if A is greater than B, you actually compare these 2 values. And if you actually meet the requirement, you will actually branch this many instructions. And jump is what happens if you get to the end. Let's say you get to the end of a function and you need to, so you have a function call, right? So you call a function in main here, and then you're going to jump down to do these instructions here. So jump says, all right, go to this instruction because that instruction tells you where to go, and this jump value is going to tell you to go back to the next instruction after that to continue your code, right? And for those of you who've had C, return 0, that's just a jump to the top of the stack. And so for this course, you're actually going to do a reduced 8-bit version. So you just really need to understand these instructions in this specific table. So the code that you've been giving has everything but how to do add I. So add, for example, you're taking 2 and 3, adding them and putting them in 1. So the encoding goes to R type, I type, and J type. Opcode tells you specifically all R types have a 6-bit opcode of 0, and then it uses the function differentiate them. So here you see there's a bit that differentiates between addition and subtraction, and has this function bit, or and set less than, which we use in comparisons, which we won't go into that much detail in this course. Then we have branch equivalents. So we have comparisons here. Jump destination, we take that 26-bit value, turn it into a 32-bit value, and go on from there. Load byte and store byte. Instead of load word and store word, since it's an 8-bit, it's a byte. So you're going to take this value and store it. So you have the instruction here. So you have this immediate value, the place pointer to the array. So you're going to add that here, and then you're going to get that location, and you're going to, from loading, you're taking the memory from that location and putting it into the local register copy, and in store you're actually taking the register and doing this calculation here and putting it in there. And so this is actually how we use, there's a specific portion that comes out of the controller. And I'll go into this a lot more. You're going to modify the controller in the data. So this is going to be the important part here. Okay. So the ALU op is going to come from the controller and go to your functions. It's going to combine this value and your function to determine a 3-bit value. In this data path, it's going to be 3 bits because it's reduced. For those of you who had me for 385, it was 4 bits. But then again, I'm not going to ask you to reproduce it on an exam. So, but these produce these specific values. This would then go to the arithmetic logic unit to tell it to do these specific instructions. Oh, I won't have you do an exam, but on a TGO, I will ask you to kind of reproduce this multi-cycle data path. But I think we'll spend next lecture doing it because I believe really going in depth into data path really is lab 3. Oh, I gotta go to content, and I'm confusing myself. Design exercises, right? I'm pretty sure lab 3 is where you'll need the controller.v file. Yep. So in that case, what we're going to do is I want to go over lab 2 real quick, just to make sure that I can kind of clarify any questions before you guys work on it this weekend. Also, from here on out, this will be the last time I ask you to do handwritten TGOs for the rest of the semester. The rest of the time, I want the TGOs included as the first page of your lab report. So I had actually started that, but the reason why I asked you to do this one is because I wanted to make sure that you guys went over, because we missed lecture, and I wanted to make sure we kept up with that. But this will be the last handwritten one, and I'll be looking. The way I'm going to be doing it is I'll be looking at the first part and putting that into your homework score, and then the rest of it will count towards your lab score. So you guys are going to be doing NAND gate layout.
How do you do the ones like 7 where it's like diagrams?
Oh, what you can do the diagram. You can take a photo of your phone and just put it in the Word document. or you can scan it. There's all kinds of ways. I don't expect you to do like a super fancy. Yeah. So in this particular part, what I want you to do, here's my advice for the layout of the NAND gate, is make sure you follow the steps very clearly. What you don't want to do is, the common mistake was you got to a certain point and something wasn't working. Like you all are figuring out, it's free, but it's worth what we paid for it, right? So it can be buggy. If you find a point where you're getting a bug, save repeatedly and go back to that previous stage, because if you start trying to do it again, you start adding more and more nodes. And if you feel you get to a point where it's just broken, save the backup copy, try again. If you still can't get it to work, write about it in your challenges section. Somebody, even though I said this last time, somebody actually sent in a lab report. We spent 40 hours on this because of this damn NAND gate. I was like, I know you've got other classes. I'm not demanding that you take that much time on this. So make sure that you make a fair attempt. But if you get to the point where it gets buggy, don't spend your life. In short, I'm not testing on your ability to beat Electric VLSI Designer, right? That's not. Show me the effort and make sure that you've made you know what a fair, honest attempt is, right? I'd be able to look at it and go, okay, they're either BSing me or not. I can look at it and go, like, there was one group that struggled. I looked at it like, oh, they were so close. I could tell they made the honest effort, and so they got the opportunity to rework on it. But don't spend too much of your time on this. I know you have other classes. I respect that. Make sure that have I made that clear? I don't want to go, I spent so much time on this. Okay. So just follow these off. I've included the CMOS rules here. Just follow these out. You'll be making a NAND gate. Make sure you read this clear. I got to find that picture. Error reference source not found. That's not good. Layout verification. Oh, yeah. So basically, you kind of get the idea. You're going to get some files and have an opportunity to work with DRC and ERC and network consistency checking. So this is basically, this part of the lab is build up your resume, make it look strong. I've done DRC, I've done ERC, and I can prove it. And then you can work on some hierarchical design and putting that in there. So you can put an inverter and work on an AND gate, and then you'll work on the full ladder, and you'll do IR sim. And then you'll start working on the ALU, which we've already covered. And you don't have to worry about the controller. So this is, yeah, so that was actually a really good point to stop in the lecture. Does anybody have any questions?
So the list of the features for
Type.
7 will be.
Yeah, the ones I covered today, put them in the lab report, and you may type them up. If it's a diagram, scan it, take a picture. So, on a side note, I wanted to mention that I'm very happy with how well you all kept up while I was out of town on these different trips. You always get, as a professor, you always get really worried. We have to do 2 weeks of lecture and have the students work on their own, like, oh, they're just going to slack off and not do anything, or are they going to keep up? And I can say unequivocally that all of you did some admirable work in terms of keeping up, and it showed in the quality of your lab submissions. So on that note, if no one has any other questions, you're dismissed.